Welcome, everyone. I'm Ralph Clayton, host of the VTM podcast. This is episode 19. Today, I want to take you into one of the greatest searches in the history of science. Exoplanets, worlds beyond our solar system. Romum, Paido, Ariel, TS, Copes. The Future Habitable Worlds Observatory, and the search for life beyond Earth. This is not simply a story about distant planets. It is not simply a story about telescopes. And it is not only a story about whether somewhere, far away, another living world may be waiting. At its deepest level, this episode asks one dangerous question. How will humanity know when it has found another living world? Because for most of human history, the planets were lights, wandering stars, sacred signs, points of motion against the fixed background of heaven. Then telescopes turned them into places. Venus had phases, Mars had a disk, Jupiter had moons, Saturn had rings, the moon had mountains, plains, craters, shadows. The sky was no longer only symbol, it was geography. But even then, the planets we knew were our own neighbors. They were members of one family, circling one star. For centuries, the deeper question remained unanswered. Were there planets around other stars? Were solar systems common? Or was our own arrangement strange, rare, perhaps almost alone? Then, in the 1990s, the answer began to arrive. Yes, there are planets around other stars. Not just one or two. Not rare exceptions. Thousands. And then more thousands. Hot Jupiters circling their stars in days. Super-Earths. Mini-Neptunes. Lava worlds. Water world candidates. Planets around red dwarfs. Planets in compact systems. Planets in wide orbits. Planets around binary stars. Planets so close to their stars that their atmospheres boil. Planets so low in density that they seem almost impossible. Planets unlike anything in our own solar system. And with that discovery, humanity entered a new age. Not the age of asking whether planets exist. That question has been answered. We now know the galaxy is planetary. The deeper age is beginning now. The age of asking what those planets are like, what they are made of, whether they have atmospheres, whether they have clouds, whether they have oceans, whether they have weather, whether they have chemistry, and whether any of them carry the one thing that would change our understanding of existence forever. Life. That is where exoplanet science stands now. Not at the beginning of discovery, but at the beginning of interpretation. The first great exoplanet era was a census. Find them. Count them. Measure their orbits. Measure their sizes. Estimate their masses. Prove that planets are common. The next era is characterization. Study them. Separate their light from their stars. Read their atmospheres. Measure their densities. Understand their host stars. Search for habitability. Search carefully for possible signs of life. That transition is enormous, because finding a planet is hard, but understanding a planet is harder. A planet does not shine like a star. It is small, dim, drowned in glare, often invisible, except through its effect on the light of its parent star. We do not usually see these worlds directly. We infer them. A star dims slightly when a planet crosses in front of it. That is a transit. A star wobbles because a planet's gravity pulls on it. That is radial velocity. A distant star briefly brightens because gravity bends light. That is microlensing. A planet glows faintly beside its star when a coronagraph blocks the star's glare. That is direct imaging. Each method is a different kind of listening. Each reveals part of the truth. Transit gives size. Radial velocity gives mass. Together, they give density. Density hints at composition. Microlensing reveals planets that may be far from their stars, even planets beyond the snow line. Direct imaging can show young giant worlds and dusty disks. Spectroscopy can reveal atmospheric molecules. No single method gives everything. This is one of the first lessons of exoplanet science. A world is not discovered all at once. It is assembled from evidence, shadow, motion, color, spectrum, timing, heat, context, and uncertainty. That word matters, uncertainty, because the search for life beyond Earth is not a field where one signal should be worshipped too quickly. A molecule can have more than one origin. A planet in the habitable zone may still be dead. An atmosphere may look promising and still be hostile. A world may have water vapor and no ocean. A planet may have oxygen without biology under certain conditions. A planet may have life and yet produce no detectable biosignature from Earth's distance. The universe does not owe us an easy answer. This is why the next generation of missions matters so much. Each mission is not simply a telescope. It is a different instrument in a larger investigation. Roman will count and image. Webb is already reading atmospheres. PL will find and characterize terrestrial planets around bright stars, especially with stellar ages and host star properties. Ariel will survey exoplanet atmospheres at scale. Chiopes refines known planets. TSES continues to find nearby transiting worlds. Ground-based giant telescopes will measure masses and atmospheres with extraordinary precision. And the future habitable worlds observatory is being shaped around the most direct version of the question. Can we identify signs of life on rocky planets around nearby stars? This is not one mission. It is a ladder. Each rung matters. The Kepler mission showed us that planets are common. TS brought the search closer to home, surveying bright stars across the sky and delivering targets. Other telescopes can follow up. ExoPlanets studies known planets around bright nearby stars with high precision, helping refine their sizes and densities. Webb can examine some atmospheres with infrared power that earlier generations did not possess. Roman will add a vast statistical census through microlensing and test advanced, direct imaging technology with its coronagraph. PLL-8 will focus on terrestrial planets around bright stars, including planets out to the habitable zones of Sun-like stars. Ariel will perform a large atmospheric survey across many types of exoplanets. And beyond them, future observatories may be built specifically to look for life. This is how the search matures, not through one heroic instrument, through a civilization learning how to interrogate the dark. Consider Roman. The Nancy Grace Roman Space Telescope is not only an exoplanet mission. It will also study dark energy and infrared astrophysics. But for exoplanets, Roman matters in two profound ways. First, microlensing. Roman will monitor stars toward the center of the Milky Way, looking for the subtle brightening caused when gravity acts like a lens. When a star passes in front of a more distant star, its gravity bends and magnifies the background light. If the foreground star has planets, those planets can leave brief signatures in the lensing event. This method is powerful because it can find planets in orbits that other methods often miss. Transit surveys are biased toward planets close enough to cross their stars from our line of sight. Radial velocity is strongest for planets that tug their stars noticeably. Direct imaging is best for certain bright, wide separation planets. But microlensing can reveal worlds at distances from their stars, more like the outer regions of planetary systems. It can help answer a census question. How common are planets, like those in the colder reaches of our own solar system? How common are planets beyond the snow line? How common are planetary systems that look, in architecture, more like ours? Roman is expected to monitor hundreds of millions of stars and reveal more than 1,000 planets through microlensing. That matters because life may not only depend on one planet in a habitable zone. It may depend on planetary architecture, giant planets, impacts, comets, water delivery, orbital stability, system history. The search for life is not only the search for Earth-sized planets. It is also the search for the story of a system. Second, Roman will carry a coronagraph. A coronagraph is a device that blocks the overwhelming glare of a star so that fainter objects nearby can be seen. This is a key technology for the future. Because if humanity ever wants to directly image Earth, like planets around nearby stars, it must solve the problem of contrast. A star can be billions of times brighter than the planet beside it. Finding the planet is like trying to see a firefly next to a searchlight from far away. Roman's coronagraph is a technology demonstration. That phrase may sound modest, but it is crucial. It is a bridge toward future missions. It will not be the final life-finding telescope, but it may help prove techniques needed for one: masks, deformable mirrors, wavefront control, starlight suppression, the ability to find faint planetary light beside the violence of a star. This is how the future is built. Not by jumping straight to the answer, by mastering the tools that make the answer possible. Then there is Webb. The James Webb Space Telescope has already changed the conversation. Webb was not designed only for exoplanets. It studies the early universe, galaxies, stars, planetary systems, and much more. But its infrared sensitivity gives it a powerful role in exoplanet atmosphere studies. When a planet transits its star, a small fraction of starlight passes through the planet's atmosphere. Different molecules absorb different wavelengths. That leaves fingerprints, a spectrum. From that spectrum, scientists can infer possible atmospheric ingredients: water vapor, carbon dioxide, methane, carbon monoxide, sulfur compounds, clouds, hazes, thermal emission. But this is not simple. The signal is tiny. The star itself can be active. Instrumental noise matters. Atmospheric models matter. Clouds can hide features. Different combinations of molecules and temperatures can sometimes explain similar data. This is why Webb has made the search both more exciting and more cautious. It has shown that exoplanet atmospheres can be probed in ways that once seemed beyond reach. But it has also shown that interpretation is difficult. This matters especially for possible biosignatures. A biosignature is not simply a molecule associated with life. It is a signal that, in context, may be difficult to explain without biology. That phrase is important. In context. Oxygen on Earth is deeply linked to life. But oxygen alone, in an alien atmosphere, would not automatically prove biology. Methane can be biological. It can also be geological. Dimethyl sulfide on Earth is associated with biological processes. But a possible detection in an exoplanet atmosphere must be treated with caution. Repeated observations and alternative explanations. The lesson is clear. There is no single magic gas, no silver bullet, no one molecule that allows us to say, without context, there is life. The search for life will require patterns: chemical disequilibrium, planetary environment, host-star behavior, atmospheric composition, climate, surface conditions if they can be inferred, geology, photochemistry, false positives, false negatives, and repeated observation. This is where Webb is so important. It is teaching us not only what we can see, it is teaching us how difficult seeing really is. It is training the science. It is forcing better models. It is identifying promising targets. It is exposing ambiguity. And ambiguity is not failure. Ambiguity is the honest beginning of a mature search. Then comes PL80. P08 is different. Its full name is Planetary Transits and Oscillations of Stars. It is an ESA mission planned to study terrestrial exoplanets, including worlds in orbits out to the habitable zones of Sun, like stars. It will use many cameras to watch large numbers of bright stars. But P08's special strength is not only planet discovery. It is the combination of planet measurement and star measurement. Because the planet cannot be understood without the star. The star gives the light. The star gives the radiation environment. The star gives age. The star gives mass. The star gives radius. The star shapes the habitable zone. The star's activity can strip atmospheres, confuse observations, or change surface conditions. A planet around a quiet sun, like star, is not the same as a planet around a flaring red dwarf. A planet that has been stable for billions of years is not the same as one in a young, violent system. Age matters. Context matters. PL80 will use astroseismology, the study of tiny stellar oscillations, to characterize host stars with high precision. That matters because many exoplanet uncertainties begin with the star. If the star's radius is uncertain, the planet's radius is uncertain. If the star's age is uncertain, the planet's evolutionary story is uncertain. If the star is poorly understood, the planet is poorly understood. PL80's gift may be that it gives us not only more planets, but better known planets. And for the search for life, better known is more important than more. 1,000 vague candidates are useful, but a smaller number of well-characterized nearby worlds around bright stars may be priceless, because those are the worlds that future observatories can study more deeply. Those are the worlds whose atmospheres may be followed up. Those are the worlds that can become targets in the next step of the search. Then comes Ariel. Ariel is ESA's atmospheric remote sensing infrared exoplanet large survey. Its mission is atmospheric survey at scale. This is another major shift. Early exoplanet atmosphere studies often focused on individual worlds. A hot Jupiter here, a sub-Neptune there, a rocky planet candidate somewhere else. But to understand planets, we need populations. We need comparison. We need to know how atmospheres differ across temperature, size, mass, stellar type, and orbital distance. We need to know how clouds form, how chemistry changes, how planets lose atmospheres, how metallicity varies, how irradiation shapes worlds, how gas giants, Neptunes, super-Earths, and rocky worlds fit into a larger evolutionary pattern. Ariel's power is not that it will answer the life question directly. Its power is that it will help build the atmospheric context. And context is everything. If you do not understand how lifeless planets behave, you cannot recognize life with confidence. If you do not understand atmospheric chemistry across many worlds, you may mistake the unusual for the biological. If you do not understand clouds and hazes, you may misread spectra. If you do not understand planet formation, you may misread composition. Ariel is part of the necessary discipline of the field. Before claiming life, science must understand planets, not one planet. Planets as a class. Planets as worlds shaped by formation, migration, radiation, atmosphere loss, chemistry, and time. This is the fourth lesson. The search for life is also the search for everything that is not life. That may sound strange, but it is true. To identify biology, we must understand abiotic chemistry. To identify a living planet, we must understand dead planets. To recognize a biosignature, we must understand false positives. A planet can fool us, not intentionally, but through chemistry, through geology, through radiation, through clouds, through the limits of our instruments. A world without life may create a signal that resembles life. A world with life may hide it. Science must be humble enough for both possibilities. This is why the phrase, habitable zone, must be used carefully. The habitable zone is not a guarantee. It is only the region around a star where, under the right atmospheric conditions, liquid water could exist on a planet's surface. But a planet in the habitable zone may be a frozen desert, or a runaway greenhouse, or airless, or tidally locked with extreme climate, or sterilized by stellar activity, or water rich beneath crushing pressure, or geologically dead, or chemically unsuitable. The habitable zone is not the answer. It is the first filter. The next question is atmosphere, then climate, then chemistry, then stability, then history, then perhaps life. This is why planetary science has become a kind of cosmic detective work. You do not simply ask, is the planet in the right place? You ask, what is its radius? What is its mass? What is its density? Does it have an atmosphere? What is the atmosphere made of? What kind of star does it orbit? How old is the system? How active is the star? Does the planet rotate? Is it tidally locked? Does it have oceans? Does it have continents? Does it have volcanic activity? Does it have a magnetic field? Does it have clouds? Can its surface conditions remain stable over geological time? And then, if the evidence allows, you ask, could life change this world in a way we can see? That is the true challenge. Not merely life existing, life detectable across light, years. Earth itself would not always have been equally detectable as alive. For much of its history, oxygen was low. For much of its history, life was microbial. For much of its history, there were no forests, no animals, no technological signals. A distant observer looking at Earth at different epochs might see very different worlds. So even when searching for Earth, like planets, we must remember that Earth has been many planets across time. A young Earth, a microbial Earth, an oxygenating Earth, a snowball Earth, a green Earth, a technological Earth. Which Earth are we looking for? And would we recognize another version? This is where future missions become so important. The Habitable Worlds Observatory is not yet flying. It is a concept for a future NASA flagship mission. But its purpose is extraordinary. It is being shaped around the direct study of potentially habitable exoplanets and the search for signs of life. This is the long horizon toward which Roman's coronagraph, Webb's atmosphere work, Pialeto's targets, Ariel's atmospheric census, TS's nearby discoveries, and ground-based spectroscopy all point. A future life searching observatory would need to directly image rocky planets around nearby stars. It would need to block starlight. It would need to collect enough photons from tiny worlds. It would need to take spectra. It would need to compare oxygen, ozone, methane, carbon dioxide, water vapor, and other possible biosignature or context gases. It would need ultraviolet, visible, and infrared capability. It would need models that can distinguish life from imitation. And it would need target lists. That is why today's missions matter. They are building the map. TSS finds nearby worlds. Scioppius refines known worlds. Ground telescopes measure masses. Webb tests atmospheres. Pileto finds bright, well-characterized terrestrial planets. Ariel builds atmospheric statistics. Roman expands the census and tests starlight suppression. Then a future observatory may ask the deepest question with sharper tools. This is how scientific revolutions are often built. Not in one thunderclap, but in layers. A catalogue, a correction, a better instrument, a target list, a failed interpretation, a new model, a disputed signal, a cleaner spectrum, a mission designed because the last mission showed what was missing. The search for life will likely be like that. Not one night when a telescope simply declares life. More likely, it will be a slow tightening of evidence. A planet found, a radius measured, a mass confirmed, a density estimated, an atmosphere detected, water vapor possible, carbon dioxide present, methane suspicious, oxygen considered, stellar activity modeled, false positives tested, additional observations taken, models argued over, independent teams disagreeing, then converging. That is not less exciting. It is more profound. Because the discovery of life beyond Earth, if it comes through exoplanets, may be one of the most carefully argued discoveries in history. It must be. The claim is too large for carelessness. To say a world may be alive is to change philosophy, religion, biology, astronomy, and humanity's sense of itself. Such a claim must survive skepticism. It must welcome skepticism. Because skepticism is not the enemy of wonder. It is the furnace in which wonder becomes knowledge. This is why we should be both excited and patient. The public wants the headline. Scientists need the evidence. The public wants the answer. The universe gives spectra. The public wants certainty. Science begins with probability. And yet, the progress is real. In one human generation, we moved from not knowing whether planets were common to cataloging thousands of confirmed worlds. We moved from guessing about distant planets to measuring their atmospheres. We moved from science fiction to direct imaging of some exoplanets. We moved from isolated discoveries to population science. We moved from asking whether other solar systems exist to asking how planetary systems form, evolve, lose atmospheres, migrate, and perhaps become habitable. That is astonishing. The search is young, very young, and still it has already changed the sky. When you look at a star now, you are not looking only at a star. You are looking at a possible system, a possible architecture, a possible set of worlds. Some scorched, some frozen, some gaseous, some rocky, some dead, some perhaps ocean-bearing, some perhaps waiting. That changes the human imagination. The night sky becomes crowded with possibilities. But possibility is not proof. That is the balance this field must maintain. Wonder without exaggeration. Ambition without false certainty. Hope without premature claims. Because the search for life is too important to be cheapened by hype. If we find a biosignature candidate, we must not turn it instantly into aliens. If we find methane, we must ask about geology. If we find oxygen, we must ask about photochemistry. If we find a planet in the habitable zone, we must ask whether it has air. If we find air, we must ask whether it has water. If we find water, we must ask whether conditions last. If we find disequilibrium, we must ask what else could create it. That is the discipline of the search, and it is beautiful, because it treats the universe as worthy of patience. So what are exoplanets and the search for life truly about? They are about distant worlds. But distant worlds are only the surface. They are about whether Earth is rare. They are about whether biology is an accident or a tendency. They are about whether planets commonly become living worlds when conditions allow. They are about whether life leaves marks in light. They are about whether the galaxy is silent, because life is rare, or because we have only just begun to listen properly. They are about whether technology can extend human perception across impossible distances. They are about whether a few photons can carry the biography of a world. They are about whether a planet's atmosphere can become a message. And they are about whether humanity can receive that message without distorting it through fear, fantasy, or impatience. Roman will widen the senses. Webb will deepen atmospheric study. Pielato will give us better, characterized terrestrial worlds around bright stars. Ariel will turn exoplanet atmospheres into a comparative science. TES and CGOPS will continue feeding the target lists. Ground-based giants will sharpen masses, atmospheres, and stellar context. And the future habitable worlds, observatory, may one day take the next great step, directly studying nearby rocky worlds for signs of habitability and life. No one mission carries the whole question. Together, they form the search. A search not only for planets, but for context, for chemistry, for pattern, for truth, for company, and perhaps, one day, for a living world whose light has crossed the darkness long before we knew how to read it. I'm Ralph Clayton, host of the VTM podcast. Thank you for joining me for episode 19 and this look into exoplanets. Roman, Webb, Pielato, Ariel, and the search for life beyond Earth. And remember, not every world in the habitable zone is alive. Not every strange molecule is a message. And sometimes, the greatest discovery begins not with certainty, but with learning how to ask the universe the question correctly.